7 Powerful Function of MOSFETs, Metal-Oxide-Semiconductor Field Effect Transistors. MOSFETs, metal-oxide-semiconductor field effect transistors, are crucial components in modern electronics due to their versatility and efficiency. Here are 7 powerful functions of MOSFETs. Switching is one of the most powerful and widely used functions of MOSFETs, metal-oxide-semiconductor field effect transistors. Here are key aspects of MOSFET switching. Key characteristics of MOSFET switching. High-speed operation. MOSFETs can switch on and off very rapidly, making them suitable for high-frequency applications. This high-speed operation is essential for applications such as pulse width modulation, PWM, in power supplies and signal modulation in communication systems. Low on resistance. When a MOSFET is turned on in saturation mode, it exhibits very low resistance between the drain and source terminals. This low on resistance minimizes power loss and heat generation, making MOSFETs highly efficient in power switching applications. High input impedance. The gate of a MOSFET has very high input impedance, requiring very little current to control the switching action. This characteristic makes it easy to drive MOSFETs directly from logic circuits or microcontrollers. Power handling capability. MOSFETs can handle significant power levels, making them suitable for switching high currents and voltages in applications such as power supplies, motor controllers, and inverters. Fast turn-on and turn-off times. The ability of MOSFETs to switch on and off quickly is crucial for minimizing transition losses and improving overall efficiency in switching power supplies and other high-speed switching applications. Applications of MOSFET switching. DC-DC converters. MOSFETs are used in DC-DC converters to efficiently step up or step down voltage levels. Their fast switching capabilities are essential for high-frequency operation, reducing the size of inductors and capacitors needed in the circuit. Motor control. In motor controllers, MOSFETs switch the current through the motor windings, enabling precise speed and torque control. This is common in applications such as electric vehicles, robotics, and industrial automation. Switch mode power supplies, SMPS. MOSFETs are key components in SMPS, which are used in various electronic devices to convert electrical power efficiently. Their fast switching reduces energy losses and improves the overall efficiency of the power supply. Inverters. MOSFETs are used in inverters to convert DC to AC power. This is critical in applications such as solar power systems, uninterruptible power supplies, UPS, and variable frequency drives, VFDs. Lighting control. MOSFETs are used in LED drivers and dimmers to control the brightness of LED lights by switching the current on and off rapidly. This method is energy efficient and allows precise control over lighting levels. Switching mechanism. Turn-on process. Applying a voltage to the gate terminal creates an electric field that attracts electrons, for NMOS, or holes, for PMOS, to form a conductive channel between the drain and source. This allows current to flow. Turn-off process. Removing the gate voltage causes the channel to disappear, stopping the current flow between the drain and source, effectively switching off the MOSFET. Advantages. Efficiency. Due to low-on resistance and high-speed switching. Scalability. Suitable for low and high-power applications. Integration. Can be easily integrated into complex circuits and systems. MOSFET switching capabilities are fundamental to modern electronics, enabling efficient power management and control in a wide range of applications. Amplification is another crucial function of MOSFETs, metal-oxide-semiconductor field effect transistors. MOSFETs can amplify weak electrical signals, making them fundamental components in analog circuits. Here are key aspects and applications of MOSFET amplification. Key characteristics of MOSFET amplification. High input impedance. MOSFETs have high input impedance, meaning they draw very little current from the input signal. This characteristic prevents the signal source from being loaded down and allows for more accurate amplification. Voltage control. The gate voltage controls the current flowing between the drain and source, allowing precise control of the amplification process. This characteristic makes MOSFETs ideal for voltage amplification. Wide frequency response. MOSFETs can amplify signals over a wide range of frequencies, making them suitable for applications from audio frequencies to radio frequencies, RF. Linear operation. In the appropriate operating region, typically the saturation region, MOSFETs provide linear amplification, meaning the output signal is a scaled version of the input signal without significant distortion. Types of MOSFET amplifiers. Common source amplifier. The most common configuration, offering high voltage gain. The input signal is applied to the gate, and the amplified output is taken from the drain. Common gate amplifier. Provides high input impedance and is used in high-frequency applications. The input signal is applied to the source, and the output is taken from the drain, with the gate grounded. Common drain amplifier, source follower, offers high input impedance and low output impedance with a voltage gain of approximately 1. It is used for impedance matching and buffering. Applications of MOSFET amplifiers. Audio amplifiers. MOSFETs are used in audio amplifiers to amplify audio signals in applications such as speakers, headphones, and audio equipment. Their ability to provide high gain with low distortion makes them ideal for these applications. Radio frequency, RF, amplifiers. In RF applications, MOSFETs amplify high-frequency signals used in communication systems, including radios, televisions, and wireless devices. Their high-speed operation and wide frequency response are critical in these applications. Operational amplifiers, op-amps. MOSFETs are used in the internal circuitry of op-amps, which are fundamental building blocks in analog signal processing. Op-amps are used in filtering, signal conditioning, and other analog computations. Instrumentation amplifiers. These amplifiers, which often incorporate MOSFETs, are designed to amplify small differential signals while rejecting large common-mode signals, making them ideal for sensor and measurement applications. Analog signal processing. MOSFETs are used in various analog signal processing circuits, such as mixers, oscillators, and filters. Their ability to handle small and large signals with precision is essential in these applications. Amplification mechanism. Operation in the saturation region. For amplification, the MOSFET is typically operated in the saturation region. In this region, the current flowing through the drain source channel is primarily controlled by the gate source voltage, VGS. Small signal model. In small signal analysis, the MOSFET's behavior can be approximated by a linear model, which simplifies the analysis and design of amplifier circuits. Advantages. Efficiency. MOSFETs can provide high gain with low power consumption. Linearity. Good linearity in the appropriate operating region, ensuring accurate signal amplification. Versatility. Suitable for a wide range of applications, from low-frequency audio to high-frequency RF. MOSFET amplification plays a vital role in modern electronics, enabling the amplification of weak signals across various applications, ensuring efficient and precise signal processing. Voltage control is another powerful function of MOSFETs, Metal-Oxide-Semiconductor field effect transistors. MOSFETs can control the voltage and current within a circuit, making them indispensable in analog and digital applications. Here are key aspects and applications of MOSFETs in voltage control. Key characteristics of MOSFET voltage control. Gate control. The voltage applied to the gate terminal of a MOSFET controls the current flowing between the drain and source terminals. This gate control allows for precise modulation of the output voltage and current. High input impedance. The gate of a MOSFET has a very high input impedance, which means it draws negligible current from the control signal. This characteristic is crucial for efficient voltage control without loading the control circuit. Linear and saturation regions. MOSFETs can operate in different regions, linear and saturation, depending on the applied gate source voltage, VGS. These regions determine how the MOSFET controls voltage and current in a circuit. Applications of MOSFETs in voltage control. Voltage regulators. MOSFETs are used in linear voltage regulators and switching regulators to maintain a constant output voltage despite variations in input voltage or load conditions. In linear regulators, MOSFETs operate in the linear region, while in switching regulators, they switch between on and off states. Analog multipliers and mixers. In analog signal processing, MOSFETs are used in multipliers and mixers to control the amplitude of signals. This is essential in applications such as frequency modulation and signal demodulation. Analog switches. MOSFETs function as analog switches to control the connection of analog signals. These switches are used in multiplexers, demultiplexers, and sample and hold circuits. Voltage-controlled oscillators, VCOs. In VCOs, the frequency of the output signal is controlled by a voltage applied to a MOSFET. VCOs are fundamental components in phase-locked loops, PLLs, and frequency synthesis. Digital-to-analog converters, DACs. In DACs, MOSFETs are used to control the output voltage based on digital input signals. This conversion is crucial for interfacing digital systems with analog devices. Programmable gain amplifiers, PGAs. MOSFETs are used in PGAs to dynamically adjust the gain of an amplifier based on a control voltage. PGAs are essential in applications requiring variable amplification, such as audio systems and instrumentation. Variable resistors. MOSFETs can be configured to act as variable resistors controlled by a voltage applied to the gate. This configuration is used in applications such as automatic gain control, AGC, and variable filters. Voltage control mechanism. Threshold voltage, VTH. The threshold voltage is the minimum gate source voltage required to create a conductive channel between the drain and source. By varying the gate voltage above this threshold, the MOSFET controls the channel conductivity and, consequently, the current and voltage. Linear region, ohmic region. When VDS, drain source voltage, is small, the MOSFET operates in the linear region, where it behaves like a variable resistor. The current through the MOSFET is proportional to the VDS, allowing for precise voltage control. Saturation region. When VDS is large, the MOSFET operates in the saturation region, where the current is primarily controlled by VGS. This region is used for stable current control and amplification. Advantages. Precision. MOSFETs allow for precise control of voltage and current. Efficiency. High input impedance and low power consumption in control circuits. Versatility. Applicable in a wide range of analog and digital circuits. MOSFET's voltage control capabilities are integral to modern electronics, enabling efficient and precise management of electrical signals in various applications. Power management is a critical function of MOSFETs, metal-oxide-semiconductor field effect transistors, particularly in modern electronics where efficiency and precise control of power are essential. Here are key aspects and applications of MOSFETs in power management. Key characteristics of MOSFET power management. Low on resistance, RDS, on. When turned on, MOSFETs exhibit very low resistance between the drain and source terminals. This low on resistance minimizes power dissipation and heat generation, which is crucial for efficient power management. High efficiency. MOSFETs switch quickly with minimal power loss, making them ideal for applications requiring high efficiency, such as power supplies and converters. Thermal stability. Advanced MOSFETs are designed to handle significant amounts of power without excessive heating, thanks to their improved thermal management capabilities. Applications of MOSFETs in power management. DC-DC converters. Buck converters. MOSFETs are used to step down voltage efficiently by switching on and off rapidly, controlling the output voltage through pulse width modulation, PWM. Boost converters. In these circuits, MOSFETs help step up voltage from a lower level to a higher level. Buck boost converters. MOSFETs enable the converter to either increase or decrease the input voltage as needed. Switch mode power supplies, SMPS. MOSFETs are integral to SMPS, which convert power with high efficiency by switching on and off at high frequencies. This includes applications like computer power supplies, battery chargers, and LED drivers. Battery management systems, BMS. MOSFETs control the charging and discharging processes in batteries, ensuring safe and efficient energy storage and use. They are used in electric vehicles, portable electronics, and renewable energy systems. Motor control. MOSFETs are used in motor drivers to control the speed and torque of electric motors efficiently. Applications include electric vehicles, industrial automation, and household appliances. Inverters. MOSFETs are essential in inverters that convert DC to AC power. This is crucial for applications like solar power systems, uninterruptible power supplies, UPS, and variable frequency drives, VFDs. Power distribution. MOSFETs are used in electronic switches and relays to distribute power efficiently within a system, ensuring reliable operation of various components. Power management mechanism. Switching mode. MOSFETs operate in switching mode for most power management applications. They switch between fully on, low resistance, and fully off, high resistance, states, minimizing the time spent in transitional states where power loss is higher. PWM control, pulse width modulation, PWM, is commonly used to control the on-off states of MOSFETs. By adjusting the duty cycle of the PWM signal, the average voltage and power delivered to the load can be precisely controlled. Thermal management. Efficient heat dissipation techniques, such as heat sinks and advanced packaging, are employed to manage the heat generated by MOSFETs during operation, ensuring reliable performance under high power conditions. Advantages: efficiency. High switching speed and low on resistance lead to minimal power loss. Reliability. Robust design ensures stable operation under various power conditions. Scalability. Suitable for a wide range of power levels, from small portable devices to large industrial systems. Integration. Can be easily integrated into complex power management systems. MOSFET's power management capabilities are essential for ensuring efficient, reliable, and scalable power control in modern electronic devices and systems. Their ability to handle high power with minimal losses makes them indispensable in applications ranging from consumer electronics to industrial power systems. MOSFETs, Metal-Oxide-Semiconductor field effect transistors, play a pivotal role in digital logic circuits, forming the foundation of most modern digital systems. Here are key aspects and applications of MOSFETs in digital logic circuits. Key characteristics of MOSFETs in digital logic circuits. High-speed switching. MOSFETs can switch between on and off states extremely quickly, which is essential for high-speed digital circuits. Low power consumption. CMOS, complementary MOS, technology, which uses pairs of PMOS and NMOS transistors, significantly reduces power consumption by ensuring that power is only consumed during the switching of states, not in the static states. High noise margins. Digital logic circuits using MOSFETs have high noise margins, making them robust against electrical noise and variations, which is crucial for reliable operation. Applications of MOSFETs in digital logic circuits. CMOS technology. Logic gates, basic digital logic gates, and/or NOT, NAND, NOR, XOR, XNOR, are constructed using CMOS technology. Each gate uses a combination of PMOS and NMOS transistors to perform logical operations with high efficiency. Microprocessors. Modern microprocessors are built using CMOS technology. Billions of transistors are integrated to perform complex computations at high speeds. Memory devices, static RAM, SRAM, and dynamic RAM DRAM, utilize MOSFETs for storing data. Each memory cell in SRAM is typically composed of 6 transistors, while DRAM cells use a single transistor and a capacitor. Flip-flops and latches. MOSFETs are used in the construction of flip-flops and latches, which are fundamental building blocks for storing and transferring digital data. These elements are essential in sequential logic circuits, such as registers and counters. Digital signal processors, DSPs. MOSFETs are used in DSPs to perform real-time processing of digital signals. DSPs are used in applications like audio and video processing, telecommunications, and image manipulation. Field Programmable Gate Arrays, FPGAs. FPGAs are reconfigurable digital circuits that use arrays of MOSFETs to implement customizable logic functions. They are widely used in prototyping, telecommunications, and custom computing applications. Application-specific integrated circuits, ASICs. MOSFETs are the building blocks of ASICs, which are custom designed for specific applications. ASICs are used in a variety of industries, including automotive, consumer electronics, and telecommunications. Digital-to-analog converters, DACs, and analog-to-digital converters, ADCs. MOSFETs play a role in DACs and ADCs, which are critical for converting signals between digital and analog forms. These converters are essential in applications like audio equipment, sensors, and data acquisition systems. Digital logic circuit mechanism. MOSFET switching. In digital logic circuits, MOSFETs operate as switches. An NMOS transistor turns on, conducts, when a high voltage is applied to its gate, creating a low-resistance path between the drain and source. Conversely, a PMOS transistor turns on, conducts, when a low voltage is applied to its gate. CMOS inverter. A basic CMOS inverter consists of a PMOS and an NMOS transistor connected in series. When the input is high, the NMOS transistor turns on, and the PMOS transistor turns off, pulling the output low. When the input is low, the PMOS transistor turns on, and the NMOS transistor turns off, pulling the output high. This complementary action is the basis for all CMOS logic gates. Advantages: efficiency, low power consumption due to minimal current flow in static states. Scalability, can be scaled down to nanometer dimensions, allowing for high-density integration. Speed, capable of very high switching speeds, enabling fast digital operations. Integration, easily integrated into complex digital systems, supporting a wide range of applications from simple logic gates to complex microprocessors. MOSFETs are integral to digital logic circuits, providing the high-speed, low-power switching necessary for the operation of virtually all modern electronic devices. Their versatility and efficiency make them fundamental to the design and implementation of digital systems. Load driving is another crucial function of MOSFETs, metal-oxide-semiconductor field effect transistors. MOSFETs are often used to drive various types of loads, such as motors, LEDs, and other high-power devices. Here are key aspects and applications of MOSFETs in load driving. Key characteristics of MOSFET load driving. High current capacity. MOSFETs can handle high currents, making them suitable for driving power-hungry loads such as motors and LEDs. Low on resistance. When turned on, MOSFETs have very low resistance between the drain and source terminals, minimizing power loss and heat generation. Fast switching. MOSFETs can switch on and off rapidly, which is essential for applications requiring precise control of the load. High efficiency. Due to their low on resistance and fast switching capabilities, MOSFETs operate with high efficiency, reducing energy loss in load driving applications. Applications of MOSFETs in load driving. Motor control. DC motors. MOSFETs are used in H-bridge circuits to control the speed and direction of DC motors. By rapidly switching the MOSFETs, precise speed control can be achieved using pulse width modulation, PWM. Stepper motors. MOSFETs drive the current in the windings of stepper motors, enabling precise position control in applications such as 3D printers and CNC machines. Brushless DC motors, BLDC MOSFETs are used in the electronic speed controllers, ESCs, of BLDC motors, common in drones and electric vehicles. LED drivers. MOSFETs control the current through LEDs, allowing for precise brightness control. They are used in applications ranging from display backlighting to automotive lighting and general illumination. Relay and solenoid drivers. MOSFETs drive relays and solenoids, providing the necessary current to activate these devices. This application is common in automotive systems, industrial automation, and home appliances. Heater control. In applications requiring precise temperature control, MOSFETs drive resistive heaters. By adjusting the duty cycle of the MOSFETs, the power delivered to the heaters can be controlled accurately. Power amplifiers. In audio and RF applications, MOSFETs are used in power amplifiers to drive speakers and antennas. Their high current capacity and fast switching make them ideal for amplifying signals. Battery management systems, BMS. MOSFETs control the charging and discharging processes of batteries in electric vehicles, portable electronics, and renewable energy systems. They ensure safe and efficient energy management. Load driving mechanism, PWM control. Pulse width modulation, PWM, is a common method for controlling the power delivered to a load. By adjusting the duty cycle of the PWM signal applied to the MOSFET's gate, the average power delivered to the load can be varied. Linear mode. In some applications, MOSFETs operate in linear mode to act as variable resistors, providing precise control of the load current. This method is less efficient than PWM but useful in certain analog control applications. H-bridge configuration. For bidirectional control of DC motors, MOSFETs are configured in an H-bridge arrangement. By switching the MOSFETs in different combinations, the motor's direction and speed can be controlled. Advantages. Efficiency. High efficiency due to low on resistance and fast switching capabilities. Reliability. Robust and capable of handling high currents and voltages. Control. Precise control of power delivered to the load, suitable for various applications. Integration. Easily integrated into complex control systems, allowing for sophisticated load management. MOSFET's ability to drive heavy loads efficiently and reliably makes them indispensable in a wide range of applications, from industrial automation to consumer electronics. Their versatility and high performance enable precise control of power in various devices and systems. Analog signal processing is a fundamental function of MOSFETs, metal-oxide-semiconductor field effect transistors, leveraging their properties to manipulate analog signals in various applications. Here are key aspects and applications of MOSFETs in analog signal processing. Key characteristics of MOSFETs in analog signal processing. High input impedance. MOSFETs exhibit high input impedance, minimizing the loading effect on the preceding stage and allowing for accurate signal processing. Linear operation. In the appropriate operating regions, MOSFETs provide linear amplification, ensuring faithful reproduction of the input signal with minimal distortion. Wide bandwidth. MOSFETs can operate over a wide range of frequencies, making them suitable for audio, RF, and other high-frequency applications. Low noise. Advanced MOSFET designs exhibit low noise characteristics, which is crucial for maintaining signal integrity in analog applications. Applications of MOSFETs in analog signal processing. Amplifiers. Operational amplifiers, op-amps. MOSFETs are used in the internal circuitry of op-amps, which are essential for a wide range of analog signal processing tasks, including filtering, amplification, and integration. Power amplifiers. Used in audio and RF applications to drive speakers and antennas with high power while maintaining signal fidelity. Mixers and modulators. MOSFETs are used in mixers to combine two or more signals, commonly used in communication systems for frequency translation. In modulators, MOSFETs modulate a carrier signal with an information signal for transmission in communication systems. Filters. Active filters use MOSFETs in combination with resistors and capacitors to achieve precise frequency response characteristics essential in audio processing, instrumentation, and communication systems. Oscillators. MOSFETs are used in oscillator circuits to generate stable periodic signals. These are crucial in applications such as clock generation, signal generation, and RF transmission. Analog multipliers. Used in applications like modulators, mixers, and automatic gain control circuits. MOSFETs enable the multiplication of two analog signals, facilitating complex signal processing tasks. Voltage-controlled amplifiers, VCAs. MOSFETs control the gain of an amplifier based on an input control voltage, used in applications such as audio signal processing, where dynamic range control is essential. Sample and hold circuits. MOSFETs are used to sample an analog signal and hold its value for a period, which is critical in analog-to-digital conversion and various signal processing tasks. Analog signal processing mechanism. Amplification. MOSFETs operate in the saturation region to amplify signals. The gate source voltage, VGS, controls the drain current, ID, providing a linear relationship between the input and output signals. Switching. For analog switching applications, MOSFETs operate as controlled switches, allowing or blocking the passage of signals based on the gate voltage. Frequency response. By designing circuits with appropriate feedback and component values, MOSFETs can be used to create filters with specific frequency responses. Advantages: precision, accurate control and manipulation of analog signals with minimal distortion. Versatility, applicable in a wide range of analog signal processing tasks, from audio to RF applications. Efficiency, high input impedance and low noise characteristics ensure efficient signal processing. Integration, easily integrated into complex analog circuits and systems. MOSFETs are integral to analog signal processing, enabling the manipulation and control of analog signals with high precision and efficiency. Their versatility and performance make them essential in various applications, from consumer electronics to advanced communication systems. These functions highlight the versatility and importance of MOSFETs in various electronic applications, making them indispensable components in both analog and digital electronics.